Welcome to my third lab report for Physics 2211. This experiment was divided into two parts. For the first part, the goal was to calculate the mass of a black hole using the data from a star's motion. We used this information for the second part, for which the goal was to find the initial velocity needed for a spaceship to navigate the black hole without crashing into it or the planet that it launched from. After the experiment, we found that the mass of the black hole was of 1.66 times 10 to the 34 kilograms, and the initial velocity of the spaceship was of -5 times 10 to the 7th, and the x component 2.9 times 10 to the 6th, and the y component and 0 in the z component meters per second. Here are the two fundamental principles that are involved in the experiment. First of all, we have Newton's second law, which defines the net force acting on a body as the rate of change of momentum over time, which can also be defined as the sum of F net parallel and F net perpendicular, both of which's formulas are written on the slide. And we also use the universal gravitational force. We have the formula right there, and we also used the formula for its magnitude. For the first part of the experiment, uh, we can see that our system was a black hole and where was only the star. We defined the conditions like the initial conditions like the star's mass and delta, which is delta time, which is 1 Earth day in seconds, so 86,400 seconds. Some key assumptions were that the only net force acting on the body was the force of gravity, gravitational attraction on both bodies. And because the force is non-constant, we can say that velocity final is equal to velocity average. Also, we can rearrange the universal gravitational force to isolate and obtain the mass of the black hole for each point in time. For this part of the coding, we filled in the definitions of momentum. So basically, all of this block right here is momentum in order to get the values that we need. Because F net is the sum of F net perpendicular plus F net parallel, we can rewrite F net perpendicular as F net minus F net parallel, which we have written right here in the code. And also we have the mass of the black hole, for which we used the formula that I mentioned before. This part of the coding is to reveal the forces that are acting on the body at each moment in time as arrows that move with the body. For our results, I found that on average, the black hole had a mass of 1.66571 times 10 to the 34 kilograms. And here are the values of F net parallel, and F net perpendicular. You can see that throughout the entire run, F net parallel was much lower than F net perpendicular. For the second part of the experiment, our system is now the spaceship, and the surroundings are both the planet and the black hole. In the code, we plugged in the mass of the black hole as well as other initial conditions that were given to us. On this part, we have the universal gravitational force redefined over and over, but changing which body is being the source and which body is being the system, so as to get the net force of each body. And we used this data to define the planet's position and velocity, as well as the ship's velocity and position using the velocity and position update formula for both bodies. Using trial and error, I decided that the initial velocity would have to be -5 times 10 to the 7th, the x component, and 2.9 times 10 to the 6th, and the y component, and 0 in the z component. And the spaceship takes the path represented by the purple line, so you can see that it goes around the black hole without being sucked by it. So some possible errors. In general, the rounding errors could have impacted the results as they accumulate over each iteration, creating bigger and bigger inaccuracies in our data. Specifically for port 1, we assume that the net force on the star is solely due to the gravitational force attraction of the black hole. And this can cause some inaccuracies because in reality, it could be created by other bodies in space that affect the star moving. And for some errors that arise for part 2 are mainly because of the method we used to obtain the data, which was trial and error. For our further questions, for what does it mean question, even though F net and the rate of change in momentum are mathematically the same, F net is associated with the acceleration and the mass of an object and can be found through the addition of all the forces that act on a body, whilst the rate of change in momentum focuses more on how momentum itself varies over each point in time. Moving on, what if we wanted the spaceship to enter a stable orbit around the black hole? For this, I changed the initial velocity, again using trial and error, and I found the values of negative 2.35 times 10 to the 6 and 1.09 times 10 to the 7 in the y component to be the appropriate for our spaceship to make an orbit around the black hole. Thank you so much for your attention.